Question 16 is about basically methods of heating things in practical organic chemistry, and this is something you absolutely have to know about in the context of oxidation of primary alcohols, but also in relation to other reactions too. So this first method is called reflux. That's the name of the method which it asks you for. Or if you like, heating under reflux is a more sort of formal way of saying that. But organic chemists tend to just talk about refluxing. Now, in this question, it drew the apparatus for you, but one of the things you absolutely have to be able to do is to draw that for yourself. So that's something that you should practice. So what you have is, first of all, you have your flask down here where the reactants are housed. Okay, so you've got your reaction mixture in here. Now this flask can either be a round bottomed flask, which is like the one drawn in the diagram in the question, or it can be what's called a pear-shaped flask, which is called a pear-shaped flask because it's pear-shaped, and the reaction mixture goes there. So either of those would be acceptable. The reason people like this one is that when you come to recover your product at the end, it tends to be sort of concentrated in this sort of narrow bit at the bottom, which makes it easier to get out than in the round bottom flask, where it kind of tends to end up stuck over the walls over a wider area. But either of those is fine, but you can't put a conical flask. So when you're drawing it for yourself, you've got to make sure you draw it right, and when you're labelling it, you should actually label it not just flask, but round bottom flask or pear-shaped flask. And then what you put in the top of it, which you can sort of draw just as an extension like that of the flask, is this central tube running up here, so that anything that vaporizes here, the vapor will run up through this central tube, and then round the outside of the tube you have this thing. And what that is a water jacket. So what happens is that you put cold water in through this pipe here, and the cold water will flow through this jacket, so it doesn't touch the vapour because you've got this wall of glass in between. But what it does is it keeps the temperature down in this part of the apparatus, because you've got this constant flow of cold water through here. The cold water then escapes out at the top there, and it keeps this glass wall cold, and the consequence is that anything that's vaporized here where it's hot will tend to turn back into liquid again here when it touches the cold glass, and the drops of liquid will just drop back into the flask. So provided you're heating at the bottom here, and provided you don't heat too strongly, you can set it up so that everything that vaporizes here gets contained within the apparatus and doesn't get to escape out the top, because it will always hit this cold wall at some point before it reaches the top, turn back into liquid and drip back down into here. And that's where the word reflux comes from. Flux is just an old word meaning boil, so it means the same stuff just keeps on boiling but then condensing and dropping back down. So it's a hugely important kind of technique, because it lets you keep on reacting for a long time without worrying about your reactant or your solvent, if you're doing it in some kind of solution, without those things just evaporating and disappearing. So that's the technique. This bit of equipment is called a condenser, for obvious reasons, because its job is to condense the vapours that come up here by providing this continuously cooled wall of glass there. So you need to label part A, which is the condenser. Part B, these little blobs down here in the bottom, these are called anti-bumping granules. And basically all they are little bits of glass. And what they do is make it possible for you to boil very smoothly, in other words, kind of simmer gently. If you don't put those things in there, there is a risk that the liquid here will sort of superheat, in other words, get heated to a temperature above its boiling point and then suddenly will vaporize all in one big rush. And that's called bumping, because then all the stuff rushes up here and you risk losing stuff out the top. So smooth boiling is an important thing, and those small bits of glass called anti-bumping granules allow you to achieve that. Okay, so those are the bits of apparatus that you need to label, and it asks you to explain the working. So, as I say, it's just about emphasizing that as substances are heated, they will inevitably tend to vaporize, but the vapors are condensed again when they hit this cold wall, which is continuously cooled by the water, and then the condensed material will drop back down into the flask so that the reaction can continue without you losing any material. The other thing that's important actually is that you have to know that when you set this apparatus up, you always put the cold water in at the bottom and have it coming out at the top. If you do it the other way around, what tends to happen is it just flows, takes the quickest route downhill, and it doesn't really fill up this top corner of the condenser, so you get less efficient cooling. So you always put the cold water in at the bottom and out at the top. In the context of alcohol oxidations, this is what you do when you want to oxidize a primary alcohol all the way through to a carboxylic acid. Because remember that the sequence of reactions is that the primary alcohol oxidizes quite quickly to an aldehyde, but then only on more prolonged treatment with the oxidizing agent, with the aqueous acidic dichromate, does that oxidize further to become a carboxylic acid. And actually that second reaction is a lot slower than the first one, so you really do have to heat for quite a lot longer to make that happen. And that's where this technique comes in, because it lets you heat for a long time without just losing your material through evaporation. So when you want to explain why you use it, emphasize that it lets you heat for a long time without losing your reactants or your products through evaporation. The method in part 2 uses the same kind of bits of equipment, but configured in a different sort of way. So again, you've got your round bottom flask. Again, a pear-shaped flask would be fine as well, with your reaction mixture and your anti-bumping granules in there, and you heat it there. And again, you're going to have a sort of tube coming out the top, like this. But the difference this time is that this tube has a side arm which comes down at a bit of an angle like that. And then at the top here, you either just close it off with a stopper of some kind, like that, and that would work fine. But what you commonly do is you stick a thermometer through that stopper, so you get something like this. Okay, so you stick a thermometer there. And we'll talk about why that thermometer is useful in a minute. Then what comes here, attached to this downward sloping tube, is a condenser, the same as you had before. So you're going to continue this downward sloping tube like that. And you're going to have your water jacket, same as we did before. And then on the end there's usually, well, there's going to be some sort of outlet pipe like this, and then some kind of collector, which could be any kind of flask there. That's the detail of that's not very important, it's this part that matters. So again, you can label this as your condenser. You can label this as your round bottom flask. So what's going to happen here? Well, what will happen is that as you heat up, again, stuff will tend to vaporize. It could be some of the reactant, it could be some of the product if you've formed it yet, it could be the solvent if you're doing this in solution. All of these things are liable to evaporation. So that vapour is going to form here and it's going to rise up this tube. It can't get out the top because you've got a stopper in it. So when you draw this, it's very important you remember to show that stopper at the top. But what the vapour can do is make its way down here. So it rises up here and then makes its way down this tube. And of course what we do with the condenser is the same as we did before. We put cold water in here and out there. And again, that will do the same as before. It will keep this glass wall in the middle constantly cold, so that the vapour coming down here will hit these cold walls and turn into liquid. But this time, of course, because of the angle on this, that liquid won't drip back into the flask. It will keep on rolling downhill until it ends up in this pot here. So this is where your product is going to be collected. Okay, so the angle there is very important. Okay, it's got to be angled downhill so that the as the liquid product is formed here by condensing on the cold walls, gravity just makes it roll down that way so that it can be collected in there. So this technique is called distillation. Okay, so it differs from reflux in that it condenses the vapour just like reflux did, but the condensed vapour doesn't make it back into the original flask. Instead it's collected in a separate vessel. So distillation is the name of the method, and in the context of alcohol chemistry, that's how you ensure that you stop oxidation of a primary alcohol at the aldehyde stage. Okay, because if you're trying to make the aldehyde, what you don't want is for that to oxidize further to the carboxylic acid. And the way you avoid that is that the aldehyde vaporizes, because aldehydes tend to be relatively volatile because they can't directly form hydrogen bonds, so that the aldehyde vaporizes and then it condenses here and is collected over there. It doesn't make it back into the flask to have another go at being oxidized further. So in other words, you can explain that this removes the product and prevents further oxidation. Okay, because the product vaporizes, the vapor condenses here and is collected over there and doesn't make its way back into the flask. So again, that's an important thing. You've got to practice drawing, labeling the bits of kit, and make sure you can explain in words how it works. Question 17 then is more practice on alcohol oxidation using this compound, butan-1-ol, as your starting material. And it asks you first of all how you would use it to make butanal. Well, butanal, remember, is the aldehyde, so that means that you have your chain of 4 carbons and an aldehyde has CHO on the end. In other words, it has the carbonyl group at the end of the chain, like that. So that's butanal. And that is what happens if you just oxidize briefly. Okay, so that's the single stage of oxidation. So in terms of an equation, that means you just need 1 magic oxygen, okay, because you're only oxidizing 1 level, not 2. So just 1 magic oxygen there. And remember, the way the oxidation works is that you're not adding an extra oxygen in there. You can see the number of oxygens is the same, but what you're doing is taking hydrogens away. So you're taking a hydrogen away from here and a hydrogen away from there to get double bond O. And those 2 hydrogens combine with the magic oxygen to make water. So that's your equation. And the key thing is that in order to stop at that stage and not get any further oxidation, you use distillation. So the key conditions are that you need aqueous acidic potassium dichromate. Okay, so you've got to learn that whole package as the oxidizing agent for alcohols. So aqueous acidic potassium dichromate, and you heat with distillation to remove the aldehyde from the mixture. before it can be oxidized further. Okay, so this idea of controlling organic reactions, because often there's more than one possible outcome, and controlling the conditions to make sure you get the outcome you want, that's a really important idea. And this is something I absolutely want you to know about. Now, to make butanoic acid, you've got to now do the opposite and make sure that it gets exposed to the oxidizing agent for a long time, for as long as it takes for all of the aldehyde that's formed first to then go on and get oxidized further. So our overall equation this time is going to be that plus 2 moles of magic oxygen. Okay, one to get to the aldehyde stage and then another one to oxidize that through to the carboxylic acid will give us the carboxylic acid, and still only one water, because that first stage of oxidation obviously produces the water, as we discussed. The second stage, you can see that all you're doing there is there's a hydrogen here in the original compound, and all you're doing is inserting an extra oxygen. You're not losing that hydrogen, so there's no other water produced. So that's your equation, and this is the same oxidizing agent, but in this case you heat under reflux. And the idea is that that allows prolonged heating without losing material through evaporation. Because, as we saw when we looked at the apparatus in the previous question, anything that vaporizes just condenses and drips back down into the original flask, so you don't lose material through evaporation. Right, question 18 tests your knowledge of alcohol reactions by giving you a product and saying, right, choose an alcohol, how would you turn that alcohol into this substance? The first one is unhelpful because it gives you the formula in the form of a structural formula like this, which is not helpful. So as always, I would be inclined to redraw that first of all as a skeletal formula so you can see clearly what's going on. So we've got CH3 and then CH, which is here, and then bracket CH3 means there's a branch, one carbon branch, and then CO like that, when it's just CO in the middle of a sequence like that, that's a ketone group. Okay, because if you think about it, that carbon, it can't be CO like that because that carbon wouldn't have enough hydrogens. So don't be fooled into thinking it's that. When you see CO in the middle of a structural formula like that, it means a ketone group like this. So that's the CO, and then CH2, CH3. So once you draw it out like that, it's much easier to see what the compound is and therefore to figure out how to make it. So that's a ketone, and what you've learned is you make ketones by oxidizing a secondary alcohol. Once you've got that, the rest is easy. So your method is going to be that you take the secondary alcohol that corresponds to that, so same carbon skeleton, but just OH in that position. Okay, be careful to make sure the bond from the carbon connects to the oxygen, not the hydrogen. You've got to draw these structures carefully. And we know that the oxidation is represented by putting a magic oxygen in to represent the oxidizing agent, and that will give you your product, which is going to be this, which is what we're trying to make, plus water, remember, as your other product, because the two hydrogens taken away from here and here combine with that to make a water. So that's your reaction, and the conditions for that: we need aqueous acidic potassium dichromate. Normally you would use a mixture of aqueous potassium dichromate and sulfuric acid, so you could say that if you wanted to. So aqueous acidic potassium dichromate, and you reflux or heat under reflux if you want to be a bit formal. Because it's a secondary alcohol, the heating conditions and not so critical as they are with the primary one, where you have alternative products. Here, the only thing you can possibly get is a ketone. But you tend to use reflux because it lets you react for a long time and not risk losing any material, so it makes sure that all of your alcohol gets converted. Second one asks us to make this compound, and hopefully you recognise this group at the end as a carboxylic acid group, COOH. Okay, so you have the carbonyl, but it has OH attached to it, so it's a carboxylic acid group. And you know that you make those from primary alcohols. So again, a good thing to do is to redraw that as a skeletal formula. You don't have to, but that's what I would tend to do, which gives you this. Okay, so that's that drawn as a skeletal formula. And you can see that the corresponding primary alcohol that you need, it just lacks the carbonyl group here. It will have the OH, but it just lacks the carbonyl group here. So you will have this as your starting compound. And what that will do is, if you oxidize it for a long time with the oxidizing agent, it will oxidize first to the aldehyde, so you get C double bond O there, and then through to the carboxylic acid, where you get C double bond O and OH at that position. So that's a double oxidation, so you need 2 magic oxygens in the equation to take you to there, and don't forget the water as the other product. So the conditions for that, again, as in any alcohol oxidation, it's aqueous acidic potassium dichromate. But this time the heating conditions are critical, because remember, if you use distillation, you would oxidize this to the aldehyde, and then the aldehyde would distill away, escape from the oxidizing agent, and never make it through to the carboxylic acid. So you must heat under reflux, because that's how you make sure it can keep oxidizing for a long time. Okay, the next one then is this compound 3,4-dichloropentanyl. So this one we have to draw the structure for ourselves. Let's do that first. Pentan then means you have a chain of 5 carbons, and the an says no carbon-carbon double bonds, and the al on the end tells you it's an aldehyde. So you have that CHO group on the end, which in the skeletal formula looks like that. And then the way it works is, if that's your ending, if you're calling it al, that defines that as being carbon 1, in case you don't have to write the 1 in. That al itself tells you that's carbon 1. So you then work backwards and say, right, that's 2, that's 3, so that's got a chlorine on, and that's 4, so that's also got a chlorine on. So that's what we're trying to make. Now it says, just make it from an alcohol of your choice. So your first thought might be, right, let's just draw the same thing with an OH there instead of a carbonyl group, put the chlorines in place, and you know, that's then easy, because you just do the standard primary alcohol to aldehyde thing. That's aqueous acidic potassium dichromate, heat under distillation. Except that won't work, because one of the things you learnt when we did haloalkanes was that if you heat that under those aqueous conditions for a long time, remember, you can substitute the chlorine with OH by reaction with water. Okay, that was one of the nucleophilic substitutions, that water can do the same thing that OH minus does and replace the chlorine with OH. It's not as fast as OH minus, but it can still do it. And so while you're spending all that time heating it with the aqueous acid and dichromate to do the oxidation, you're going to replace those chlorines with OH, and that's not going to give you the product you want. So you've got to find a different way of doing it. And whenever you see 2 chlorines next to each other in a molecule like that, what should spring into your mind is that if you had an alkene group, you could just add chlorine across it to put those 2 chlorines in there when you need them. So there's probably more than one way, or there is more than one way to do this question, but what I would suggest is that you start with that. Okay, so where the 2 chlorines need to be in the end, for the moment, you just put an alkene group there and say, right, that's the alcohol we're going to start with. Because what you can then do is do the oxidation to the aldehyde, which will give you this. Okay, so it's making the aldehyde group where we want it, and it's just keeping this safe in the form of an alkene for now. So that is what we've just been learning about. So that's aqueous, acidic, potassium dichromate. Always that whole package you need. And you have to specify how you're going to heat it, because it's always got to be heated. And remember, if it's a primary alcohol, that's particularly important. If you want to stop at the aldehyde stage and not make a carboxylic acid, you need to use distillation conditions to make sure that you separate this from the reaction mixture before it can oxidize any further. So that's the first step. And now that we've got that there, now we can turn our attention to this and just add chlorine across the double bond. And there are no special conditions for that. Remember, alkenes react very easily with halogens, so you just add Cl2 and you'll get your product. Okay, so then we have this compound, which is an alkene. And remember, we've got to make it from an alcohol, and you know how to do that. You do it by an elimination reaction, in which you heat the alcohol with concentrated sulfuric acid, which acts as a dehydration catalyst. So it's concentrated sulfuric acid and heat. And the alcohol needs to have an OH at one end of where we want the alkene group to be and a hydrogen at the other end. So you could basically use one of two possible alcohols, which either had the OH there or the OH there. So we can write down both of them. So we could have our OH here. Okay, so drawing all those atoms there that are going to be there in the alkene at the end up here, and just have OH and H there that we're going to eliminate. Or we could do it the other way around and say, right, we want all those atoms here, again, like this. Or, but we could have the H there and the OH here. Okay, and then eliminate like that. And that will give some of the same product. Both of those are problematic because if you eliminate the OH from here, the hydrogen won't necessarily come from there. It could come from here or here. So you're going to get a mixture of products. Likewise, if you have the OH there, the hydrogen could come from here, which is what you want, but it could come from there. So neither of these is perfect, and there's no obvious way to tell which one is going to be better. So you could have either one of those alcohols, and that's the key condition you need to remember. You've got to make this slightly strange looking molecule, but actually of course there's nothing very strange about it. It's just a normal haloalkane, except that there are 3 bromines and not just 1, but they're all just going to behave the same way. So really all we need to do is to think, right, well, let's start with a molecule that's the same as that but just has OH where the Br is. So we get this. Okay, so instead of a tribromo compound we have a triol, like that. And then really all you have to remember is how do you substitute Br for OH, and it will just do the same thing to all 3 of them. And the answer is that you need sodium bromide and conc sulfuric acid. Which is the standard way for turning an alcohol into a haloalkane. You have either sodium bromide or sodium chloride plus conc sulfuric acid, and that will do the job for you. In terms of an equation, because we've got 3 OHs, that means we need 3 H pluses, which come from the conc sulfuric acid, and 3 Br minuses, which obviously come from the NaBr, and you put all that lot together and you'll get this plus 3 HBr. Here's your other product. And that's it. So that's an example of a question which was actually really easy. It's just that because the molecule looks slightly scary, it makes it seem trickier. But you've got to just practice a lot so that you don't get phased by those little tricks that they will try to pull.